So, in the last class, last lecture, we had derived the correlation for mass transfer from a particle. Okay, we had defined the dependent dimensionless group, the scaled flux, which is the flux divided by a quantity with the same dimensions as the right side of Fick's law, and we had two independent dimensionless groups, the Reynolds number, which is the ratio of inertial and viscous effects, and the Peclet number, which is the ratio of convection and diffusion. And if you recall, in the last lecture, I had said that when the Peclet number is small, diffusion is dominant and convective effects are small, then the fluid velocity and the flow properties no longer affect the transport, and therefore, the Sherwood number has to be a constant. In the limit of high Peclet number, where convection effects are dominant, even though there may be the flow may be very fast past the particle, flow itself cannot transport mass to the particle because the flow is along the surface, is tangential to the surface, and there can be mass transported from or to the particle only if there is a component of the flux perpendicular to the surface, which is absent as far as fluid flow is concerned, and therefore, diffusion has to be important even in the limit of high Peclet number. We then were looking at the heat transfer in a heat exchanger. Okay. So, in this particular case, we have fluid flow, okay, through the tube side of a heat exchanger, and the temperature difference is characterized by the difference between the average temperature of the fluid and the temperature of the wall, which is assumed to be a constant in this case for simplicity. The quantity that we would like to predict, the dependent parameter, is the average flux, the total heat transfer rate per unit area of the entire tube. Okay. And this average flux, okay, the parameters that it depends upon are, of course, so the dependent parameter is the average flux. Okay, which I will call QAV. Okay. This can depend upon independent parameters, the temperature difference, okay, which we had already denoted as delta T, okay, the diameter and the total length of the pipe, okay, the total length of the pipe. It should be the length only within the heat exchanger. Okay. It can depend upon the diameter D, the length L. It can also depend upon the flow properties, because as the fluid is going through, basically the heat transfer is taking place across the wall of the pipe, okay, and at the wall of the pipe there is basically fluid flow that is happening tangential to the surface. So, basically convection is bringing in heat, okay, tangential to the surface, and then conduction is transporting that heat perpendicular to the surface. Okay. So, therefore, the average flux can depend upon the flow properties, that is the velocity. In this case, I will call it as the average velocity, okay, the average velocity of the fluid in the heat exchanger. Okay. The flow properties, density, rho, viscosity, mu. Okay. And in addition to this, there are the thermal properties which determine the rate of transport. Thermal properties are the specific heat and the thermal conductivity. Okay. So, there is the thermal conductivity, and the specific heat. Cp. So, these are the first one is the dependent dimensionless group, dimensional parameter, and the rest are independent dimensional parameters. Okay. So, one can write down the dimensions of each of these. Okay. The heat flux, energy transported per unit area per unit time. Okay. So, if you recall, the heat flux is equal to the energy per area into time. Okay. Let us not confuse. Okay. Energy is mass length square T power minus 2. Okay. That is the force into distance, and area is length square, time is T. Okay. So, the dimension of this is m T power minus 3. Okay. That is the dimension of the average heat flux. Temperature difference, of course, has dimension theta. Okay. Okay. The dimension of the temperature difference is this dimension theta. Okay. The diameter has dimension L, the length has dimension L. Okay. Velocity has dimensions distance per unit time, density is mass per unit volume, viscosity we had already calculated as mass per unit length per unit time. Okay. If you recall, we had done this using from Newton's law for viscosity. You can go back and refer to the lecture there in order to see how this is derived. Thermal conductivity. Okay. Okay. The thermal conductivity comes from the equation for the heat flux. Okay. The Fourier's law for diffusion, QAV is equal to minus. Okay. If you recall, if you have fluid layer of thickness delta Z and I apply a difference delta T across the two ends, okay, the heat transferred is going to be from the surface of higher temperature to the surface of lower temperature. It is proportional to the area and it is proportional to the temperature difference, inversely proportional to the thickness. Therefore, if I define the flux as the heat transferred per unit area per unit time, it has to be proportional to the temperature difference, inversely proportional to the distance. The constant of proportionality is the thermal conductivity. Okay. And we just got the dimension m T power minus 3 as the dimension for the heat flux, has to be the dimension of the conductivity times theta by L. Okay. Therefore, the dimension of the thermal conductivity is m L T power minus 3 theta inverse. Okay. m L T power minus 3 theta inverse. And the specific heat. Okay. Specific heat we get from the expression m Cp delta T is equal to the thermal energy. Well, it is actually the enthalpy, but it has the same dimension as energy. Okay. So, therefore, I have the mass dimension, the dimension of the specific heat and the dimension of temperature is equal to the dimension of energy, which is mass length square T power minus 2. Okay. Therefore, the dimension of specific heat is length square T power minus 2 theta inverse. Okay. So, that is the dimension of the specific heat. Okay. So, now in this problem we have 1, 2, 3, 4, 5, 6, 7, 8 independent dimensional parameters and one dependent dimensional parameter, and it has 4 dimensions, okay, mass, length, time and temperature. There should be 5 dimensionless groups, 1 independent and 3 1 dependent and 3 independent dimensionless groups. We can simplify the problem when there is no interconversion between mechanical and thermal energy. Okay. For the special case where there is no interconversion between mechanical and thermal energy, you can simplify this problem further by considering the mechanical and the thermal energy as 2 different dimensions. There could be interconversion due to fluid friction, for example. Okay. Viscous friction will generate heat and heat up the fluid. However, if the heat transfer rate due to the temperature difference is much larger than the heat generated due to fluid friction, then there is we can assume that there is no interconversion. Okay. The flow velocity and so on are all mechanical properties, the density, viscosity, they depend upon mechanical energy. Whereas the flux, the thermal flux and the thermal conductivity and so on are thermal properties, and they depend upon the heat energy. We can consider the heat energy as a dimension different from mass, length, time and temperature. Therefore, for defining thermal properties, we will use the heat energy, and for defining mechanical properties, flow properties, we will use mass, length and time. Okay. So, this gives us a modified dimension, okay, for this problem. Just as we had considered the solute mass and the fluid mass to be different dimensions in the previous problem, we will consider here the thermal energy to be different from the mechanical energy and define a different dimension h for the thermal energy. Okay, we will define a different dimension h for the thermal energy. Okay. The heat flux then, okay, is the thermal energy transported per unit area per unit time. Okay. Therefore, in this modified dimension, the thermal energy has to be the heat transported per unit area per unit time. Okay. The thermal energy transported per unit area per unit time. Okay. And this also changes the definition of the thermal conductivity, because as you recall, Fourier's law for heat conduction is Q is equal to K delta T by delta Z with a negative sign. Okay, it was Fourier's law for heat conduction. And if I define this left side as thermal energy per unit area per unit time, this has to be the dimension of K times theta divided by L. Okay. Therefore, the thermal conductivity has dimensions of H L inverse T inverse theta inverse. Okay. You multiply throughout by L, divide throughout by theta, okay, and you get the dimension of the thermal energy. Okay. Similarly, the definition for the specific heat also changes. Okay. If you recall, the specific heat was defined as the thermal energy which has dimension H is equal to m Cp times delta T. Okay. And what that implies is that H is equal to mass times the dimension of specific heat times the dimension of temperature. Okay. Therefore, the specific heat has dimension H m inverse theta inverse. Now, with this modification, we have 5 dimensions: the thermal energy, mass, length, time and temperature. Okay. And 5 dimensions, there should be only 3 independent dimensionless groups and 1 dependent dimensionless group. Okay. And so, we can see we can derive all of those one by one. Okay. The first dimensionless group, okay, it has to the independent dimensionless group. Okay. It has to contain the average flux scaled by thermal quantities. Okay. And we could go through and scale it either by the specific heat or by the thermal conductivity and some combination of temperature difference and length and so on. Okay. But an easier way to do it is to realize that Fick's law of diffusion relates the flux to the temperature difference divided by the characteristic distance. Okay. And therefore, the Fick's law of course applies only locally, okay. But however, the dimensions on both sides of Fick's law are the same, okay. Therefore, I can get an independent dimensionless group just by scaling the average flux by the quantity with the same dimension as the right side of Fick's law, okay. That is, I can scale the average flux by a quantity with the same dimension as the right side of Fick's law, which is the thermal conductivity times the temperature difference divided by a distance, and this has to be a dimensionless group, okay. And this dimensionless group is what is called the Nusselt number, the dimensionless flux, okay. So, the Nusselt number is basically the ratio of the average flux divided by a quantity containing the thermal conductivity and temperature difference divided by the diameter, which has the same dimension as the right side of Fick's law, okay. So, the independent dimensionless group in this case is the Nusselt number. Okay. The independent dimensionless group is in this case the Nusselt number, okay. And I said that we have to have one independent and three dependent, this is the dependent dimensionless group. This is the quantity that we want to find out, okay. And the independent dimensionless groups are those that contain quantities that are already specified. The independent dimensionless group, one of them is quite easy, okay. Since you have two quantities with the same dimension as length, okay, I can write an independent dimensionless group as d by L, okay. The ratio of two lengths is dimensionless, okay. So, that d by L is an independent dimensionless group. The second one is also what we have seen before, okay, Re, which is equal to rho V average d by mu. The Reynolds number is rho V average d by mu. And then there is a third dimensionless group which contains the specific heat, okay, which we have not yet, okay, used in any of the dimensionless groups so far, okay. We have used the thermal conductivity, the density, viscosity and so on, all the length scales, but one quantity that we have not yet used is the specific heat, okay. And we can get a dimensionless group involving the specific heat as follows, okay. Okay. So, I can define the dimensionless group involving the specific heat, okay, okay, as some combination. See, the specific heat contains a temperature dimension in it, okay. The only other quantities that contain the temperature dimension are the temperature difference and the thermal conductivity, okay. So, because of that I can either scale the specific heat by the temperature difference or by the thermal conductivity. If I scale it by the thermal conductivity, then the heat energy dimension also cancels out, okay. The heat energy dimension also cancels out if I can scale the specific heat by the thermal conductivity, and then I get a quantity that depends only upon mass, length and time, okay. So, if I define this, okay, as Cp by mu, right, times something, okay, times some quantity, okay, Cp by mu, Cp by k times something, I am sorry, okay. Then you can see that this, the dimension of this is h m inverse theta inverse, okay, by h L inverse T inverse theta inverse, okay. The energy dimensions will both get cancelled out and the temperature dimension will both get cancelled out, okay. And therefore, the Cp by k has dimensions of m inverse L T, okay. the Cp by k has dimensions of m inverse times length times time. Okay. And you can see that if you had to multiply Cp by k times this quantity here, the viscosity, okay, you would get a quantity that is dimensionless, okay, because Cp by k has exactly the inverse dimension as the viscosity, okay, m inverse Lt. Okay. So, I could just multiply Cp by k times the viscosity to get a dimensionless number. Okay. That is the third independent dimensionless number that I require, okay, for this problem. The third one is Cp mu by k. It is called the Prandtl number. The Reynolds number was ratio of inertia and viscosity. Okay. We will see a little later that the Prandtl number is the ratio of momentum diffusivity and mass diffusivity. We will see that a little later in this course. Okay. Nevertheless, the correlation that I get now is the Nusselt number is equal to some function of the Reynolds number, the Prandtl number, and this ratio of lengths d by L. Okay. So, this is going to be the form of the correlation. Okay. The ratio, the Reynolds number, the Prandtl number times the ratio d by L. Okay. And the Nusselt number is any function of this, of these parameters. Okay. So, based upon dimensional analysis and an additional simplification, okay, dimensional analysis plus the assumption that the heat energy is a different dimension separate from the dimension of the mechanical properties. Okay. Because of that, I could get a correlation that depended only for the dimensionless flux, the dependent dimensionless number. So, the dimensionless flux that depends only upon three parameters: the ratio of the diameter and the length, the Reynolds number, and the Prandtl number. Okay. So, we have significantly simplified the problem in this case. Now, what would be, so we had made this assumption that there is no interconversion of energy. Okay. If there were interconversion of energy, right, if there were interconversion of energy, what would the other extra dimensionless number be? Okay. So, let us examine this in a little bit. Okay. If there were interconversion of energy, then the other dimensionless number would basically be a ratio of the thermal energy transfer rate and the mechanical energy dissipation rate. Okay. The thermal energy transfer rate and the mechanical energy dissipation rate. Okay. The thermal energy transfer rate, okay, energy transferred per unit area per unit time. Okay. The thermal energy transfer rate QAV is equal to the energy transferred per unit area per unit time. It has the same dimension as, okay, so let me just write this. The dimension of this is equal to, okay, it has the same dimension as K times delta T by L. Okay. Or in this case we should use the diameter because that is the, okay. This has dimensions of mass, okay, T power minus 3. Okay. We had just calculated that. The thermal energy transfer rate has dimensions of mass times T power minus 3. What about a mechanical energy dissipation rate per unit surface area that has the same dimension? As I said, there is conversion of mechanical energy to heat energy due to viscous dissipation. Okay. So, therefore, the dissipation rate per unit area into time. This is a dissipation rate per unit area of the surface of the tube, okay, per unit time. Okay. Okay. This has to have the same dimensions m T power minus 3, okay, and this can depend upon the parameters, the viscosity, okay, the velocity and the diameter. Okay. It can depend upon the parameters viscosity, velocity and diameter, okay, because the dissipation rate is basically determined by viscosity. Inertia is a conservative force, it does not dissipate energy, it is only fluid viscosity that dissipates energy due to fluid friction and causes drag. Okay. So, this is the energy dissipation rate. This has dimension of m L inverse T inverse, this has dimensions of L T inverse, and this has dimension L. Okay. By a combination of these three, I need something that has exactly the same dimension as this energy dissipation rate per unit area per unit time. Okay. And you can easily see that this can be obtained if I write the combination as mu times V square, okay, V by D. Okay. Mu has dimensions of m L inverse T inverse, right. I multiplied by length square, by velocity square, L square T inverse, okay, and divide by L. You can see that the length dimension will exactly cancel out. You will get mass to the first power and time to minus 3 power, okay. T inverse from viscosity and the square of T inverse from the velocity. Okay. So, this is the rate of dissipation of energy, okay, and I can divide these two, okay, to get a ratio of the rate of energy dissipation per unit surface area and the rate of energy transfer due to conduction per unit surface area. Okay. That is called the Brinkmann number. Okay. So, this is basically mu VAV square by K delta T. If this number is small, the rate of viscous dissipation of energy is much smaller than the rate of conduction of energy, and in this case you can consider that there is no interconversion of energy between mechanical and thermal energy, and therefore, you can consider the heat energy and the mechanical energy as two different things, two different dimensions. If this number is not small, then you cannot make that assumption, and the Peclet number, the correlation for the Sherwood number, for the Nusselt number, would also depend on this Brinkmann number. Okay. The correlation would also depend upon this Brinkmann number. Okay. So, this one we solved for the heat transfer in a pipe. Okay. We will come back and look at this in further detail a little later on. Okay. Similar can also a similar analysis can also be used for heat transfer from a particle, for example. Okay. In that case, you have only one length dimension, there is only one length dimension d, okay, and the average flux, okay, I can define the Nusselt number as QAV, heat energy transported per unit area per unit time, divided by K delta T by D. Okay. And this Nusselt number will be a function of the Reynolds number, okay, and the Prandtl number. Okay. Okay, I can write it as a function of the Reynolds number and the Prandtl number, where the Reynolds and Prandtl number are basically defined for the particle, okay, where V is the velocity of the particle and the Prandtl number is equal to Cp mu by K. Okay. The Prandtl number is just equal to Cp mu by K, it is a fluid property. Okay. And if the Reynolds number is small, then the flow around the particle has no effect on the heat transfer rate. Okay. If the Reynolds number is small, then the flow around the particle has no dependence on the, does not depend, has no effect on the heat transfer rate, and therefore, in this case, just as we had said that the Sherwood number is equal to a constant, okay, in the case of the flow past a particle. In this case, the equivalent condition is that the Nusselt number is a constant. Okay. I can redefine the dimensionless numbers a little bit in this case. Okay. So, rather than writing it in terms of the Reynolds number and the Prandtl number, okay, I can define another dimensionless group, okay, the Peclet number, okay, which is equal to the Reynolds number times the Prandtl number. Okay. And you can see that if I multiply the Reynolds number by the Prandtl number, what I will get is rho Cp V d by k, okay. Rho Cp V d by k. Okay. This parameter, okay, k by rho Cp, okay, is equivalent to the diffusivity that I had in the mass transfer problem. We will see that this is a thermal diffusion coefficient. Okay. If this Peclet number is small, that means that convection is much smaller than diffusion. Okay. If this Peclet number is small, okay, if the Peclet number is much smaller than 1, then convection is much smaller than diffusion. And in that case, the Nusselt number has to be equal to a constant. Okay. In that case, when the Peclet number, the ratio of convection and diffusion is small, the Nusselt number has to be a constant, and of course, that value of the constant has to be calculated. Turns out that it is equal to 2, just as the Sherwood number, okay, for reasons we will discuss a little later, when the Peclet number is small. When the Peclet number is large, convective effects are dominant, but because thermal conductivity results in heat transfer perpendicular to the surface, whereas flow results in heat transfer only along the surface, there can be no transport of heat from the surface due to thermal conductivity due to the flow, and therefore, the Nusselt number depends upon the Peclet number even in the limit of high Peclet number. Okay. You cannot neglect diffusive transport even when convective effects are strong, just as we had seen in the case of mass diffusion from a particle. Okay. And if the Nusselt number is a constant, then you can easily find out for example, the heat transfer rate by relating the average flux is equal to some constant, okay, into k delta T by T. Okay. Just heat transfer rate is equal to a constant into k delta T by T, and that you can use in order to find out what is the average heat transfer rate. We will continue this a little in the next lecture and go on to the other problem that we had, okay, that is for the flow in the pipe. We of course want to predict the average flux depending upon all the flow properties, but we also want to know how much energy is required to drive the flow in the pipe, because the flow in the pipe has to be driven by a pressure difference across the ends of the pipe. Okay. How much energy is required for that? How do we estimate that? It is a momentum transfer problem. We will look at using dimensional analysis to predict what is the pressure difference required for a given flow rate in the next lecture after completing this section. I will see you then.